Einsteinium, the 99th element of the periodic table, was discovered in the fallout of the first hydrogen bomb, detonated by the United States in the Marshall Islands on November 1, 1952. This highly radioactive element has never been studied in detail, despite being a byproduct of the most destructive weapon humans have ever created. Because the element can only be synthesized in extraordinary environments like the blast zone of a thermonuclear explosion, scientists have long struggled to make enough Einsteinium in laboratory conditions to unravel many of its basic properties. Now, a team of researchers has used modern techniques to pin down key chemical information about Einsteinium for the first time using a 200 nanogram sample of the element. The results reveal new insights about Einsteinium and offer a window into the unusual behavior of the actinides, a radioactive family of elements spanning the atomic numbers 89 to 103, according to a study published on Wednesday in Nature. We now have access to state-of-the-art advanced techniques that weren't there in the past few decades, said Rebecca Abergel, a nuclear engineer at UC Berkeley who co-led the new research, in a call. Everything came together only recently. Einsteinium has been experimentally studied before, but previous tests inferred information about the element from the radioactive signatures of small samples. Abergel and her colleagues set out to conduct a spectroscopic analysis that would reveal finer details, such as the bond distance of Einsteinium, a property that influences how an element interacts with other atoms and molecules. It's a very typical type of information you'd want to get about any element, said Abergel. It tells us about how an element is going to be behaving when it's surrounded by other atoms, and how it's going to form chemical bonds. There are only a few elements in the periodic table where we don't have this kind of information, so this is about building up some fundamental knowledge and contributing to our understanding of how different elements behave, she added. The team received a sample, made by the Oak Ridge National Laboratory's high-flux isotope reactor in Tennessee, in the fall of 2019. They initially had to adjust their experimental technique to account for the fact that the sample was contaminated with californium, another actinide element. Once that kink was worked out, the element was examined using the molecular foundry at Lawrence Berkeley National Laboratory, Berkeley Lab, and the Stanford Synchrotron Radiation Light Source, SSRL, at SLAC National Accelerator Laboratory. Even as everything came together on an experimental level, the researchers faced another unforeseen challenge: the COVID-19 pandemic. We got pretty lucky that all of the experimental work reported in the paper was done before March 15, Abergel said. I think the last data collection was around March 10 or so, and we were shut down in California a few days later. The sample contained Einsteinium-254, an isotope of the element with a half-life of 276 days, so the abandoned substance was like a ticking clock, decaying away until it would no longer be useful. The samples just sat around for a few months in their shipping container, Abergel recalled. We got back to it early summer so that we could recover what was left and hadn't decayed, and reprocess it so we could potentially do other studies. But at that point, there wasn't enough to do anything chemically driven again. We've turned back to other kinds of experiments where you rely on radioactivity detection, she continued. That's what we've been doing since the summer. In spite of the disruptions, the researchers have provided the first in-depth look at this mysterious element, including finding its bond distance, while also shedding light on its actinide relatives. Abergel, who serves as the heavy element chemistry group leader at Berkeley Lab, hopes that these advances will lead to future experiments that probe the most enigmatic members of the periodic table, or even discover entirely new super-heavy elements. This is really a data point and we need to build upon that, she concluded. What's exciting is that I think we are charting the path for studying those elements.